Hello guys, today we're going to be covering section 3.3, which is derivatives of trigonometric functions. I just want to start off by saying I'll be skipping a section on this, mostly because it's just a pain and it's not really important. And I might cover it in a different video if you guys really want. It's a geometric proof of a limit, but once we get there, I'll explain why. So, first things first, we want to find some derivatives of trigonometric functions. Like, look at the function just sine of x. We want to find what the derivative is. Like, what is f prime? So, the first thing that we can do is, try to hypothesize what it is. Like, what is f prime of x? Oof, that's a weird looking f. But, we can try to guess from the graph, actually. So I'm going to try to draw the graph of sine of x. So it's going to go from, it's going to go between -1 and 1. It's got a 0, pi over 2, pi over 3. Nope, that's not pi over 3. It's 3 pi over 2. My bad. 3 pi over 2 and 2 pi. We're just going to work on those points, right? So sine of 0 is 0. Well, actually, let me just draw some dots. That's not black. So, this is going to be for the curve, sine of x. So sine of 0 is 0. Sine of 1 is pi over 2. The sine of pi, 0. Sine of 3 pi over 2, -1. Sine of 2 pi, 0. So let's see how well I can draw the graph. Let's see. All right, so this is good enough. So, one of the ways that we've kind of touched upon briefly is talking about, how can we get the derivative, or how can we get the derivative of f of x based off its, slope, or based off the graph of it. So again, like what we did, let me just do one thing before we start. Remember that, technically sine of x takes in all real numbers. So this is, the domain, I guess you could say, of f is like, all real numbers. So just kind of keep that in mind. And remember, one of the things is that, x is in radians. I think you could probably switch, like, typically you can, if you really, really wanted, you could define sine of x to be in degrees instead of radians. But that's just a pain. No one does that. Just keep it in radians. So anyways, just, kind of ignoring that. Those are more just technical things to kind of keep in mind of what, what we're doing when we try to find the actual derivative. But anyways, so, let's actually try to find, like the derivative based off the graph. So remember, the derivative is the slope at each point. So if we start at 0, if we look, that kind of looks like the line y equals 1. Well, that y equals x. So this looks to have like a slope of like 1. If we look at pi over 2, that's a horizontal line. So the slope looks like it should be 0. What about pi? If I drew that well enough, that should be -1. At 3 pi over 2, looks like it should be 0. At 2 pi, looks like it should be 1. So, what happens if we plot those values and try to connect the dots? So this is -1, 1, so 0, pi over 2, pi, 3 pi over 2, and then 2 pi. I want to move this there. That should be good. So now let's plot the points. So at 0, we had a slope of 1. At pi over 2, we had a slope of 0. At pi, we had a slope of -1. At 3 pi over 2, we had a slope of 0. And at 2 pi, we had a slope of 1. So I'm going to connect the dots now. So this is going to be the graph of f of x, well, a graph of f prime of x. Remember, it's not going to be perfect, but this is just to get at the idea. So what does this look like? Kind of looks like cosine. Say it looks pretty similar to cosine. So, it looks like, f prime of x is equal to cosine of x, but I'll put a question mark around it, like above the equality, just because you don't really know. But that's kind of what it looks like. Let's look at it. It looks like our guess. So the first thing we need to do to actually, find the derivative, we could just do the definition already, the limit definition. But in order to use the limit definition, we have to get a bit more technical about some stuff. But what I mean by technical about kind of stuff is that we have to show some limits first. So, let's start off by saying, can we verify? All right. So one of the ways we could do to verify this is, actually look at the limit definition. And what we're going to need to know first is, these two identities. Well, we're going to start off with just proving, we're going to assume one is true. The limit of sine of theta, divided by theta is equal to 1. So that's the first thing we're going to need to know. And there is a geometric proof that's in the book. It's in the notes. Well, it's in the it gets in the PowerPoints that you guys have access to. And it's just geometrical. It's based off of a circle. And I don't think we're going to use that. And I'm going to look, I haven't checked the homework just yet, but I feel like it's not there because I don't really see it would be there. That the, thing is relating to the proof of this. So I don't think we need to know it. So let's just say proof left for the reader. Oops, left for the reader. Or, you can check the PowerPoints. Because I went over this in the lecture, even though this is a bit late. But it's not really it's a bit technical. I wouldn't really want to waste your time with it. But the second one that we can actually use, that's actually more useful, is one that we can prove nicely. It doesn't require any geometrical arguments. Is this one right here. The limit as theta goes to 1, not theta goes to 1, but theta goes to 0 of cosine of theta minus 1 divided by theta. And remember, and let me just kind of reread this one out, is that the limit as theta goes to 0 of sine of theta divided by theta is equal to 1. So the way we want to do is let me just kind of put it in a different color. We want to evaluate this limit. We want to figure out what it is. So, if we plug in 0, we're just going to get 1 minus 1, which is just 0, divided by 0. So, not useful. It means we got to do more algebra. So, we're going to multiply by the conjugate. We get cosine of theta plus 1 divided by cosine of theta plus 1. And that'll be equal to the limit as theta goes to 0 of cosine squared of theta minus 1 divided by theta times cosine of theta plus 1. And this is where we're going to have to use some, like, the trig identities that we have. So the first one's going to be just the fact that cosine of squared of theta plus sine squared of theta is equal to 1. So this right here will be equal to, like, just negative sine squared of theta based off that identity. Identity, yes. So we get is negative sine squared of theta divided by theta times cosine of theta plus 1. And that'll be equal to the limit as theta goes to 0. So what I'm going to do now is just, break up the fraction. Well, not really break up the fraction, but write it, put some pieces together or pull some pieces apart. So I'm going to move like one sign over here and the other sign, I guess you could, I don't know how you want to draw that. And this is multiplication. I should put the parentheses there to indicate that. So what I'm going to be doing is we have, well, first off, I'm going to put the negative out there. We can just pull the negative out. But we have the sine of theta, which is going to be one of these, divided by that theta, times by the other sine of theta, divided by that cosine of theta plus 1. So in both of these cases, the limits exist. So we can break up the limits over them. So it's negative the limit as theta goes to 0 of sine of theta divided by theta times by the limit as theta goes to 0 of sine of theta divided by cosine of theta plus 1. And the fact that I put the negative on the first one doesn't really matter. You just put the negative somewhere. And what that's going to give us. So, again, just ignoring that negative for a moment. Maybe you could put it on the outside again if you want. You can move it in. You could put it anywhere you want. But the trick is that this right here is an identity that I just told you about. The one that I said, proof is left with the reader if you want to learn more. So we have the limit as theta goes to 0. Sine of theta divided by theta is equal to 1. So this right here is equal to 1. So we get negative 1. And then here, everything here is continuous. We're not going to divide by 0. So really what we get is just sine of 0 divided by cosine of 0 plus 1. That's just 0 again. So this is equal to 0. So what that tells us is that 0 is equal to the limit as theta goes to 0 of cosine of theta minus 1 divided by theta. And let me just kind of box that to make it clear. I usually like to write this at the end, just kind of be clear whenever I'm doing work. But, let's just write it in a box to let you guys know it's important. So we have limit as cosine theta minus 1 divided by theta as theta goes to 0 is equal to 0. It's a very nice formula. Very nice. I wouldn't say you need to remember this one as much. Like, it's important, but not as important. But this one right here, I would say, please remember. Because that one likes to show up a lot. We're going to do another example with it. But, it's pretty nice, so please remember it. So, why are we going over these limits again? Well, I'll show you why. Let's start off by actually, doing the thing that I wanted to do to begin with. Was whenever f of x is equal to sine of x, we want to find f prime of x. So that was our goal to begin with. So f prime of x is equal to d of dx of like cosine of x, well, not cosine of x, of sine of x. But remember the definition, is the limit as h goes to 0 of sine of x plus h minus sine of x divided by h. And there's a trig identity here that's, what that's equal to is that we'll have like a sine of like a plus b is equal to sine of a times cosine of b plus sine of b cosine of a. That's the one we're going to be using right here. So we're going to use it with sine of x plus h. So what's going to give us is sine of x times cosine of h plus, looks like cosh. And it's going to be plus sine of h cosine of x. And you know what, let me just use a different color, just kind of indicate that these are in parentheses, that these are the arguments. Sometimes people get confused. Some people accidentally divide by just the function, just sine, which is a math sin, so please don't do it. And then remember at the end we have the minus sine of x. And still all over h. Alright, so the next step I'm going to do is just break up the fraction into nicer pieces. So again, there's not always intuition on how to do this. It's usually just trial by error or just experience. Typically you want to put things together that, that look nice. So here's like a sine of x and here's another sine of x. So I want to put them together. So we're going to get sine of x times cosine of h, because this sine of x comes with that cosine of h. Then minus that sine of x, and then divide by that h. And the last one that we have, the last remaining piece that we have is the sine of h times by the cosine of x, all divided by that h. And now we're just going to break up the limit over them, because each of these limits will exist. And one of the things I want to note is that the sine of x here and sine of x here do not depend on h, and this cosine of x doesn't depend on h. So we can pull them out. We can treat them as constants and pull them out of the limit. So that's what we do when I rewrite the next line as well. So just to be clear, I'll say pull this out, pull this out, pull this out as well. I'm not going to say they all go in the same spot, but we can just move them out of the limit. So what I mean by that is that we have the sine of x times the limit as h goes to 0 of cosine of h minus 1 divided by h plus cosine of x times the limit as h goes to 0 of sine of h divided by h. All right, and now if you remember the limits as before, we have, what we said before, that this right here equal to 0. And then the last piece, the sine of theta goes to 0, sine of theta divided by theta is equal to 1. And remember that the fact that theta, we have thetas versus h's, you can just let theta equal h. You get the same form. So this right here is equal to 1. So what that tells us is to get the sine of x times 0 plus cosine of x times 1, which is this, which in totality gives us, just cosine of x, because, it's just cosine of x times 1. And what that tells us to begin in the end, that we have the derivative of sine of x is equal to cosine of x. So this is very beautiful. I love this very much. And this is probably going to be the ones that you'll have to remember. And, likewise, what we can do is, we can do the same thing for cosine of x. Say it's going to be the similar approach. We get that d of dx of cosine of x is equal to negative sine of x. So the derivatives are equal to each other, sort of, but they're negatives of each other instead. So, that's pretty nice, actually. And, this is the one you'll have to remember. But, now I've just done 2 trig functions. What's the next one that's natural? Tangent. So actually, let me box these to make it clear. Box. I'd say please remember if you can. And then let me just do, oops. Sorry, I just gotta check my notes. Okay. Okay, sorry about that. So the next thing we want to do is differentiate, tangent of x. Now on to tangent of x. And remember what tangent of x is equal to. That's equal to just sine of x divided by cosine of x. So this is why we're moving on to it. Oof, that's some horrible handwriting. It's because I'm not used to, whenever I write my sines, I usually don't write the parentheses. I'll just write sine of x divided by cosine of x. But I think it's kind of important to write those parentheses. So, like that. Okay. So, we're going to prove this one again. This one right here would be a good one to remember. I mean, not a good one to remember, but it's a good one to know the proof. If you can do the proof for this, then that's pretty awesome. Whenever I took calculus in high school, actually, this was on my test. And funnily enough, I didn't remember something, one of the proofs, or one of the details on the proof. I just I think this is true, and I got full credit on it. I'll explain what it was. But, so, tangent of x is equal to sine of x divided by cosine of x. But one of the things we just covered was, the quotient rule. So, to find, the derivative of dx of tangent of x, we use the quotient rule. So that's actually pretty nice. So, let's actually use that. So I like I say, whenever I like to use the terminology, it's low d high. So cosine of x times the derivative of sine of x. Let me stick with this notation so I don't use the prime. So it's the derivative of sine of x minus, now it's going to be high, so sine of x, d low, so d of dx of cosine of x. And it's all going to be over low squared, so all over cosine of x squared. I'll just write it like that because my parentheses suck. All right. So now using the definitions that we just used, or the formulas that we just used, or just found, so we get cosine of x, the derivative of d of dx of sine of x. That's going to be cosine of x. So times cosine of x. And the last one we had was, remember that d of dx of cosine of x is equal to negative sine of x. So this is going to be negative sine of x. And then this right here, like I just said, negative sine of x. So these negatives will cancel. And what we get, is still all over cosine squared of x. But actually, I'll write this right here. This notation is a bit better. So what I get is cosine squared of x plus sine squared of x, all divided by cosine squared of x. And what is the top equal to? The top is equal to 1. And that's the thing whenever I took calculus, whenever I try to prove this on a test, I was just I didn't know that. I didn't have a good trig teacher. So I was I think the top is equal to 1, but I don't remember why. And I just said it's equal to 1, cosine squared of x, and it's because this right here literally does equal to 1. It's one of those really nice, beautiful trig identities. I'd probably get that tattooed on me. But, now that we have this, What is that equal to, though? Just secant squared of x. Because, secant is equal to 1 over cosine, so that's just secant squared of x. So, just to be clear, we get that this is equal to d of dx of tangent of x. And I'll box it in red, because this is, again, one of the ones you need to remember. The other ones I'm about to list, they are important, but honestly, I don't remember them off the top of my head sometimes. The only one I really remember is secant, but they all kind of follow a pretty similar structure. So for the remaining trig functions, we're going to get is just a few more, identities that we can just prove using the quotient rule. All right. And again, you can verify this on your own. And actually, I'd probably recommend verifying these derivatives on your own, because it's just good practice. And it's cool to do math and verify identities. I like doing it. So the first one is the derivative of cosecant of x is equal to negative cosecant of x times cotangent of x. And the next one's going to be d of dx of secant of x and the derivative of secant of x is equal to secant of x tangent of x. So I think these are pretty similar, where this is cosine, this is sine. The derivative of sine is equal to the negative cosine. So that's why we get the negative here. And I don't know, I like these, because these are they're the same form. We keep the secants. We keep the argument. One has a negative, one doesn't have a negative. And one has tangent and the other one doesn't have tangent. Also, I don't know, I like to think the derivative of secant is secant tangent. I don't know why, that just sounds pretty awesome to me. But moving on to the last one, d of dx of cotangent of x. As you can probably guess, as the last one was equal to, secant squared of x. And what you can kind of see from a relationship here is that it's going to be negative cosecant squared of x. So, these are pretty nice. I like them, actually. And I'll box them in red to kind of indicate their importance. These ones you probably don't need to remember too much. As long as you can prove them, it's very helpful. So I'd recommend proving them. Usually proving things can kind of help you understand why they are true, or maybe help you remember them too. So I definitely recommend doing that. And then, let's move on to some examples real quick, because, I haven't really given you a lot of examples, just a lot of math. So let's differentiate the following functions. So, the first one I'm going to do is f of x is equal to cosine of x plus x squared sine x. All right. So so far, it looks like it's going to have a product rule in it, and, some of the trig derivatives that we just talked about. All right. So f prime of x is going to equal to d of dx of cosine of x plus d of dx of x squared times sine of x. Oof, That's bad. There's some notation for like brackets that look like this. And man, mine always looks so horrible. Let's hope we never get there. But, keep on going. We said the derivative of cosine of x is equal to negative sine of x. And now what we need to do here is remember that, the product rule. So what it's going to be is, the derivative of the first times the second. So, well, actually, let me write it down a bit more consistently. So d of dx of x squared times sine of x plus d of dx of, now this time it's going to be flipped, so derivative of sine of x times the other function x squared. Oops, I just got an email. Great, another email, okay. Sorry about that. So, let's keep on trucking. Trucking. I think that's the phrase. All right, so the derivative of x squared, 2x, so times sine of x. Then the derivative of sine of x is equal to negative cosine of x. Oh, no, not negative cosine. It's equal to just regular cosine of x. Then times x squared. So then let's just simplify now. Let's pull out some sines. And again, kind of like what I've told you before, that you can just stop right here. You're good to stop right there. That's fine. You don't need to simplify. I just like to simplify. So there's a sine, here's the sine. So we'll pull out that sine of x. What we'll get remaining is a 2x and a negative 1. And plus that cosine of x times x squared. And we can leave it like that. So I'll just put like a little good to stop here sign. And the reason why is because I'm not asking you to simplify more than you need to. Again, like I don't want to waste your time doing things that you should already know. I mean, not to say if you don't know them, that's anything bad, but just like I'm not testing you on your pre-calculus, only your calculus. So you're going to get more points for getting the correct derivative, and once you get the correct derivative and you accidentally mess with the algebra, I'm not really going to care. All right, so our second function that we're going to differentiate is going to be h of x is equal to cosine of x divided by 1 minus sine of x. And so h prime of x is going to equal to, remember this is going to be a quotient rule, so low d high minus high d low all over low squared. So it's going to be low d high, so the derivative of cosine of x. I'm just going to jump into it and just say, well, actually I'll write the prime notation now. Minus high, so cosine of x, d low, so then 1 minus sine of x all over low squared. So what we're going to get is 1 minus sine of x times the derivative of cosine of x is equal to negative sine of x minus cosine of x, and now the derivative of 1 minus sine of x. Remember we said the derivative of sine of x is equal to cosine, but then we have the negative out there, so we get negative cosine of x. And what this comes down to is that, again, so ideally in these kind of situations, you'd want to simplify, but you don't necessarily, oops, I forgot the bottom. 1 minus sine of x squared. Yeah, so typically, like if you stopped right here, that'd be fine. Ideally, I'd want you to keep going in these kind of situations, especially with trig identities. And as I keep going, you'll see why. So I'm just going to go ahead and distribute the sine of x and, simplify everything. So we get like negative sine of x then negative sine of x times negative sine of x is going to be plus sine squared of x. Then we have negative, negative right here, so these are going to be positive. So plus cosine squared of x, and then all divided by 1 minus sine squared of x still. And remember what I said last time about this? This is equal to 1. So we just get it is equal to 1 minus sine of x. All I did was just swap them around. Get 1 minus sine squared of x. Wait, why did I write that squared? That's not supposed to be there. My bad. It is wrong. I was like, that's not supposed to be right. Because what it is that one of these will cancel with that, leaving you just 1 over 1 minus sine of x. It is beautiful. I love it. So that's the correct answer right here. And, that's just another example. Like, if you wanted to stop here, this is fine. But ideally, it's kind of nice, especially with trig functions, if you keep going. And, just see if you can simplify it. In this case, we could simplify it. And it's not always the case where you can simplify. And, the reason why I'm saying you can stop there is because, there's probably some trig identities that you just don't remember. And if you don't remember them, then, that doesn't mean you're doing math wrong at all. So, and as long as you remember the derivatives and all that stuff, then I'm fine with that. So the last example we're going to cover is we're going to evaluate a limit. So we're going to evaluate the limit as x goes to 0 of sine of 7x divided by 4x. And, I'm going to write it in red what the limit we had earlier was. And the limit as theta goes to 0. Oops. And it was sine of theta divided by theta, and that's going to equal to 1. So, if we look at the differences between these two, is that sine of, that's awful. Sine of theta divided by theta. So if you look at these two, these are the same. Like the argument of sine of theta is being divided by that theta. So, that's actually pretty nice. But here we do not have the same. They're not the same thing. So we need to be able to, make them the same or make them look pretty similar in order for us to get that limit. And we might get some extra stuff in the end, and that's just a byproduct of what's happening. So let's do the limit as x goes to 0 of sine of 7x divided by 4x. So this 4 right here, we can move it, we can, just take it out, do 1 over 4 instead. And then, again, we want to use the limit, but we need whatever is inside the sign to also be on the bottom. So you can put that, let's just say we put that 7 there. And again, we can't just multiply by 7 willy-nilly. We also need to, multiply. We can't just divide by 7. You also need to multiply by 7. And to make it clear what I'm doing right there is that I'm really multiplying by 7 over 7, which is equal to 1. I'm putting this 7 into right here. And then for the last 7, I'm going to move it out here with that 4. So then what we get is the limit as, x goes to 0 sine of x, sine of 7x divided by 7x is equal to 1. So we just get 7 over 4 times 1 is equal to 1. And let me formalize it for you. Let me just rewrite that in a very clear, different way. So we get the limit as x goes to 0 of sine of 7x divided by 4x. That's equal to, I'm going to pull out that 4 now. The limit as x goes to 0 of sine of 7x divided by x, and then we want that 7 there, so divide by 7, and then we can pull out that 7 again, like I said before. So it's going to be 7 over 4 times the limit as x goes to 0 of sine of 7x divided by 7x. This goes to 1. Well, that's equal to 1, actually. It's not goes to 1. It's equal to 1 instead. So we just get 7 over 4. And one of the things you might ask is, why does it matter that here we have x going to 0, but for the other example, we didn't have that? Like here we have x goes to 0, but here we have 7x. If we look at this case right here, we have theta goes to 0, and here we have, the same thing. We all have the same values. In reality, that doesn't really matter too much, because it's not that it's not like they go to different places. So it's like we can do as x goes to 0. Well, actually, like even if you look at 7x going to 0, like let's just say 7x goes to 0. Like if 7x goes to 0, then obviously x has to go to 0 too. So even though they're not the same, they're not exactly the same, they still go to the same place. So it's okay. And, that's pretty much it for this example. And then that's kind of the key things, especially with these problems right here, is you want to write them in a way that allows you to use the things that you've already know. But that's it for this section. There's nothing too really difficult about this. A lot of these derivatives you probably want to memorize, especially these ones right here, the sine of x and the cosine of x one. And it would be nice for you to remember these limits. This one's really nice. And knowing how to prove it's also pretty nice. It is ideal to remember how to prove it, but if you don't remember it, you don't remember how to do the derivative of it, or you don't remember the limit of it, that's fine too. But preferably, please remember the one that I clearly boxed and wrote please remember on. And, the proof of that, if you want to look into it, again, that's also it's in the PowerPoint. If you want to know more, feel free to email me, and I'll give you a proof for it. But, that's it, guys. Like, comment, and subscribe, I guess. Sorry for the slightly late video, but adios.